stage.
Thank you, Mr. Chairman. This is where I live. This is close, at least, where I live. It's located. Cagliari is located in an island in Italy, which share, at least in part, with Malaysia, the warm weather, and the pristine seawater, as you may see. So it's a nice place. Come and visit me. And I would like also to thank, first of all, Dr. Sundram for inviting me and all the organizing committee for being so kind in all the organization, and also to give me the opportunity to talk about what one of the fields I'm working in research, the influence of dietary fatty acid on the endocannabinoid system. So what are the endocannabinoids? I mean, by the name you may guess what they are, but they are bioactive lipids derived, again, from arachidonic acid. We have seen yesterday, talking about other products, the so-called oxygenated eicosanoids. So they are mainly anandamide. Most of you know the origin of the name ananda, and which is an amide of arachidonic acid, and also a monacylglycerol of the arachidonic acid, as you may see. But why they are called endocannabinoid? Because they are the endogenous ligand of the cannabinoid receptors, which the name derived from because they bind also an exogenous bioactive compound present in cannabis. And those cannabinoid receptors, they started to be famous for the brain, and we will see later the activity. But actually, it's present not only in the brain, but also in adipose tissue, muscle, liver, intestine, pancreas. And also the CB2, very similar kind of receptor, but different. They are mainly present in the immune system. And how they are formed, it's interesting because the arachidonic acid to produce anandamide comes from position 1 of the phospholipids. And we will see this is it's an important issue, and just get attached to phosphatidyl ethanolamine and attached to the amino groups to form this what called NAPE. So then it's hydrolyzed by a phospholipase D and also by other pathway to form the anandamide. Monacylglycerol, the same. It's in this case, the arachidonic acid comes from position 2 of the phospholipids. Then through different hydrolysis, you have the monacylglycerol, the 2-arachidonyl glycerol. And it's interesting because they don't accumulate, actually. They are immediately hydrolyzed by different enzymes, the fatty acid amide hydrolase, mainly for the anandamide, and monacylglycerol lipase for 2-arachidonyl glycerol. So they are produced, so-called on-demand, so when they need, and they bind to CB1 or CB2 receptors, but also to other receptors. And so the endocannabinoid biosynthesis, the receptor CB1 and their degradation, they all make the endocannabinoid system. So why are interesting in the field of nutrition? Because they have a synergistic effect, the endocannabinoids, especially when there is an overactive endocannabinoid system. In the central system, at a hypothalamus level, it's enhanced hunger, and at the nuclear accumbens, it's increased the motivation to eat and to search for calorie-dense food. That's quite interesting because also involved the rewarding effect. So this is why the drug, the cannabis works, because increase the gratification, the rewarding effect. And it's interesting because then instead at peripheral tissue decrease the energy metabolism. So what is the net result? It's an increase of food intake with great rewarding effect, and increased fat storage because there is less energy metabolism. And so at the end, if, after years and years of overactive endocannabinoid system, you will end up to increase fat storage, excess fat storage, and dyslipidemia, and what is called now metabolic syndrome. So why it's important that they are formed from arachidonic acid in position 1 and position 2, and they give it both different endocannabinoids, because as you know, most of the arachidonic acid is present in position 2. That's why in tissue it's more produced to AG respect to anandamide, but as you know, they are both. They can be influenced by the diet. So we can modify the precursor, arachidonic acid, in the phospholipids by dietary means. And how? How? Because you know that omega-3, omega-9, omega-6 are competing because they share the same enzyme to be metabolized, but also for incorporation in phospholipids. So if you have more omega-3, you will have less omega-6. If you have less omega-6, omega-3, you will have omega-9 in the case of deficiency of essential fatty acid. So they are competing. So you can work by dietary means, having a different concentration of arachidonic acid in phospholipids. In fact, there are several papers being published since 2001 where it has been shown that dietary fatty acid actually can modify the endocannabinoid biosynthesis. And especially omega-3, and as you know, and we heard the previous speaker talking about the omega-3 fatty acid, the health benefits. So the question is, does dietary omega-3, by modulating the endocannabinoid system, affect metabolic syndrome? So some of the effects of the omega-3 can be ascribed to a modulation of the endocannabinoid system. So we did a study in an obesity model, in a visceral obesity model, Zucker rats, and clinical studies in obese and overweight subjects. So Zucker rats is a model of visceral obesity. They are essentially, they have an inactivated mutation in the leptin receptors, the hypothalamus level. So this is induced hyperphagia. They eat the double respect to normal rats, so they get fatter and fatter. After 4 weeks, they get visceral obesity, very similar to what happened in humans with a low-grade inflammation, fatty liver. And it's interesting, this model, because to explain, we have to come back a little bit to adipose tissue physiology. As you know, the fat is accumulate, and we are very good in store fat in adipose tissue. And most of the fat we store is in the subcutaneous adipose tissue with respect to visceral adipose tissue. This is in a physiological condition. And this is why, because there are several signaling where favor the incorporation in subcutaneous adipose tissue with respect to visceral adipose tissue. Some are hormonal, the estrogen, for example. So that's allowed women to increase their fat store in the more physiological way in subcutaneous adipose tissue. But also it's more sensitive to PPAR gamma, which increase triglyceride accumulation and pre-adipocyte differentiation, but also it's more sensitive to insulin. So it's, it will increase the accumulation of triglyceride in postprandial state, and also will limit the release of the free fatty acid after a postprandial, but will increase the release in only fasted state. On the opposite, visceral adipose tissues, less sensitive to PPAR gamma, less sensitive to insulin, more sensitive to adrenergic system. We might say that the visceral adipose tissue is more a transient adipose depot, and it's more sensitive to adrenergic system. And as a previous speaker said, what happened during stress, we have an increase of visceral adipose tissue, and also you have an increase of release of fatty acids from the visceral adipose tissue, which for the anatomical position will increase the fatty acid release via portal vein in the liver. And so you will increase tissue fatty acid uptake all over the tissue. So the net results in this case will be accumulation of fatty acid, while in this case will be mainly beta oxidation, because this is in the state where there is no glucose. So this is a physiological way. Of course, when you increase the visceral adipose tissue, will increase what is called the ectopic fat. So why this is important in the with the endocannabinoid system? Because endocannabinoids activate PPAR gamma. And what is interesting that it has been shown that in obese people, in visceral obese people, there is an increase of endocannabinoid in visceral adipose tissue. So there will be an increase of triglyceride deposition with continuous release of free fatty acid independently of insulin, and so you will have ectopic fat accumulation. And also there is a kind of, there will still also fat from subcutaneous adipose tissue, because usually in this case the endocannabinoids are low, so you will have the situation of increasing visceral adipose tissue with then recruitment of cytokines, of macrophages, so you will have at the end also the low-grade inflammation. So what we did with Zucker rats, then we gave omega-3 in two forms, actually. We heard before talking about fish oil, but also we use another supplement with krill oil, which is closer to what is the omega-3 in the food, because it's, there is a certain percentage bound to phosphatidylcholine and a part as a triglyceride. So we wanted to compare two different forms, one more typically in the supplements, and this one is, even though it's a supplement, but also closer to what we have in the food. So we did a tree diet, a control diet, which matched the tree diet for alpha-linolenic, for linoleic and oleic acid, and the fish oil krill oil diet were matched for EPA and DHA, and of course the ratio in 6 and 3. And actually the concentration of EPA and DHA was not so high, because we wanted them to compare to what is in humans. So the results were quite interesting, because as it has been shown, krill oil has a higher bioavailability of omega-3 in the phospholipids fraction, as you may see, and also there was a decrease, but the same level of arachidonic acid. But interesting, the two endocannabinoids, was much lower with krill oil, but also with fish oil for anandamide, while DHA only with the krill oil. Interesting, this is in visceral adipose tissue, but then in subcutaneous adipose tissue, we didn't see any difference in endocannabinoid system, and also we didn't see any difference in the changes in the fatty acids. It seems, therefore, that subcutaneous adipose tissue is more resistant to changes to dietary supplements. And therefore, what we would expect by these results is that the endocannabinoid levels between these two compartments of adipose tissue is changed, so we would expect a lower release of free fatty acid, a lower decrease of attack deposition, and maybe a lower topic fat accumulation. As a matter of fact, when we check for liver, as you may see, there is a big difference. This is a classical, you see, fatty liver. And omega-3 diet was, the fat was much lower, as you may see here, and krill oil even more efficient than fish oil to decrease deposition in liver. But not only in the liver, we check also in the heart, and actually, as you may see, krill oil was able to decrease triglyceride accumulation also in the heart, and also in muscle. So we extended the study in two clinical studies. The first one was just to make sure if giving krill oil was able to decrease endocannabinoids. And as you may see, we confirmed that overweight and obese people had a higher level of endocannabinoids And it was interesting to see that there was a decrease, in this case not significant, of anandamide, but 2-AG in the obese people decreased significantly. So this was just for weeks, so was not sufficient to see any other effects. In another study, this is another pilot study. I was forgetting that we found also a good relationship between the ratio in 6 and 3 of highly polyunsaturated fatty acid and 2-AG. So we did another study. This is a very pilot study now. Is in progress a much larger study using krill powder. So giving a total of about 400 milligrams per day of EPA-DHA. And this study lasted 24 weeks. It was interesting because, as you may see, it was a steeply decrease of anandamide at week 12 and especially at week 24. But interesting, there was a decrease in triglyceridemia because those were patients that were not only mildly obese, they were also hypertriglyceridemic patients, individuals. And also was decreased, even very mild difference, waist-hip ratio, which is correlated, as you know, to visceral adipose tissue. Liver density was decreased, but was not significant. So maybe should last longer, or maybe with more patients that may become significant. So it seems like that also in humans, it reflected what we have seen in rats. The next question is, it's only omega-3, only EPA and DHA. So in this study, we gave sheep cheese, naturally enriched in alpha-linolenic, CLA, and vaccinic acid. Why naturally? Because this has been enriched by modifying or not modifying the diet of the sheep, in the sense that if they eat just grass, they will naturally increase alpha-linolenic, conjugated linoleic acid, and vaccinic acid. And we did it in hypercholesterolemic subjects, mildly overweight. So it was interesting because, as you may see, this is the fatty acid composition, and there was a decrease of saturated fatty acid, about 23%, and there was an increase, actually, because vaccinic acid is a trans fatty acid, there was an increase of trans fatty acids, and especially vaccinic, as you may see, and also there was an increase, of course, of alpha-linolenic acid and also of CLA. Then the question of one of the referee was, okay, but you got these nice results because you are replacing the saturated fatty acid with polyunsaturated fatty acid. But actually, when we made the calculation, the saturated fatty acid was mainly replaced by trans. So we shouldn't have this kind of effect. Mainly 60%, more than 60% vaccinic acid. So that was a strange situation, and then we will see the data. And the experimental design, we gave 90 grams of enriched cheese. There was a crossover study. 90 grams of enriched cheese, then wash out for 3 weeks. Then the control cheese, and the same the crossover. So the same happened to the other group. Was interesting. Why only 3 weeks? Because the ethical committee, they told us you cannot give 90 grams of cheese to hypercholesterolemic patients because, as you know, doctors, the first thing they say that avoid cheese, avoid any product with saturated fatty acid. We repeated also with 45 grams of rich cheese. So what we have seen that the plasma levels of vaccinic acid CLA increase in the enriched cheese, in the case of CLA also in regular cheese. These are products that are formed in the rumen of ruminants, but also increase alpha-linolenic acid, as you may see, and also EPA. So, and the results of the increase of alpha-linolenic acid, EPA, the increase of vaccinic acid, and CLA was the decrease of the ratio omega-6, omega-3 of the highly polyunsaturated fatty acid. So that's why then we made a comparison with the previous studies, and we checked for anandamide in 2-AG. 2-AG decreased, but not significantly, but anandamide decreased almost about 50%. So then we check if those effect on endocannabinoid was also having an effect on lipid metabolism. And actually, we have seen that enriched cheese decreased significantly total cholesterol and cholesterol LDL. So there was some effect on this. So we may conclude that, I will show, so that decrease of substrate for endocannabinoid biosynthesis, as also demonstrated by others, decrease endocannabinoid biosynthesis by entry long-chain PUFAs, but also not only that, but also reduce the activity of the endocannabinoids. So will decrease, especially only when the endocannabinoid system is overactive. We can say that not only omega-3 long-chain PUFA, but any dietary strategy that aim at increasing this N3 and 6 long-chain PUFA fatty acid may reduce the overactive endocannabinoid system. So this is an important issue. So it's not important how, but it's important always all the diet. That's why, dietary fatty acid, not as a single, often we concentrate with one single fatty acid. Okay, we concentrate on saturated fatty acid, we concentrate with trans, which has to be in a balance. So probably we are seeing that they work, sometimes fatty acid work, dietary fatty acid, they work in combination, they work synergistically. So it's important to see all over the diet. This is sometimes it's a problem of discrepancies between animal studies and human studies because it's important, the background diet. And what would be important because that means that a physiological control of the endocannabinoid system will control different aspects of lipid and energy metabolism. I would like to thank the many collaborators I had in these studies, and last but not least, I would like to thank all my coworkers in my lab. Thank you very much.
Thank you, Dr. Sebastiano, for your presentation. Now the floor is open for questions.
Sebastiano, that your observation with the krill oil versus the fish oil, you expect that because of the phospholipid absorption, or could it be also related to the astaxanthins present in krill oil?
Okay, that's a very good question. I was afraid to get to put also studies that we ran on simple on phospholipids, pure phospholipids, omega-3 bound. And the results were quite similar. So we might say that most of the data are from the phospholipids, omega-3, but we cannot rule out that also astaxanthin might have a role, because this is an important issue because it has been shown, there are different studies showing that actually astaxanthin has this kind of effect. And astaxanthin in the krill oil is peculiar because it's de-esterified, so it's protected. And also in this case, we have studied, we have data, interesting data, showing that in this form, it's more bioavailable. So we cannot exclude, probably astaxanthin will contribute to this. Yes, but still the phospholipid form, as I shown, it's more bioavailable on the phospholipid. It's interesting because there are studies showing also that dietary phospholipids, they can go almost intact in the phospholipid, in tissue phospholipids.
Dr. Sebastiano, thank you again. Just clarification. Are we 100% certain that these compounds that you mentioned, the anandamides, are actually metabolites of arachidonic acid? Is that fully confirmed now?
Yes. I mean, that they are from arachidonic acid,
Right.
you mean? Yes, yes.
Yep, okay. And the leading question to this is, in the research that's been done, has anybody looked at how these metabolites can affect the overall cyclooxygenase pathways, particularly the prostacyclin thromboxane cycling and ratios in the body?
That's a very good question because it has been shown that anandamide actually is a substrate for cyclooxygenase or lipoxygenase. This is very important for one point because with the same pathway, if you have in position 1, instead of arachidonic acid, you have palmitic, which is, as you know, in position 1, it's more common, or oleic acid, you have two other products, two other amides, which they don't bind to CB1, but they bind to PPAR alpha. So they have a completely different effect. In some cases, for example, the OEA, the oleal congener of anandamide, actually has an almost opposite effect. So if you think that arachidonic acid and anandamide can be somewhat be metabolized by lipoxygenase or cyclooxygenase, will increase the level of the other two. So it's a matter of balance. This is a really important issue that we are studying on this because we all know that all the cyclooxygenase, the lipoxygenase with the phospholipase A2 pathway, but this is in this case will be from the pathway in position 1.
Thank you very much.
Thank you.
Just a quick comment. If I'm correct, the CB1 and CB2 also involved in vascular actions as well. Isn't that correct?
Yes. I mean, they have so many activity, and most of the studies, most of the people working on endocannabinoids and some of my co-works, they were mostly concentrated in brain because everything started with tetrahydrocannabinol, you know, the active compound all the psychotropic effect. Only relatively recently it has been shown in peripheral tissues, and now they are discovering several activities. That's why we think it's important, you know, the synergistic effect between brain, central, and peripheral tissues, but also in the vascular. Yeah.
Any more questions? We have time for one more question. One.
All right, fine. I got to get this in. Representing some of the media in North America, and everyone wants to know, how do we infer, by the way, I don't think I've ever seen, admittedly, an obese flamingo, so I like that idea of putting astaxanthin into a formula. To Dr. Talbot's point earlier on, maybe some formulators in the audience here realize the complexity of palm oil. We just add a little astaxanthin in there, and we've got a weight loss formula here. But so that's to that end. Let me actually frame it this way. If you had full support for a research study, how would you take red fruit palm oil to do a weight loss study? And is that even possible?
You know, I'd expect this kind of question because it's really important. We didn't study still palm oil, and hopefully we will have the opportunity to see what would be the impact of palm oil on the endocannabinoid system. There are a lot of potential in that. We have some study, and there were two preliminary to show here that endocannabinoids will have some, let's say, some interference with carotenoid metabolism, for example. So carotenoids may play a role, but also alpha-tocotrienol could play a role. Besides, as I said before, palmitic and oleic acid are precursor of other kind of congeners of endocannabinoids with very different effects, with very positive effects. So it would be really interesting to see and to study what would be the impact of red palm oil. I would say, rather than to study different fractions, I would take it as a whole, because probably this is, would be the most of the effect. So sometimes maybe for scientific purpose, we like to separate different fractions, but the food is one. So we are, you know, our evolution is made by food, not by single components. So sometimes we shouldn't forget this. Thank you.
Thank you very much.
Thank you.
I would like to call upon Professor Dr. Manorama Kanuri. Dr. Manorama Kanuri received his MSc in Foods and Nutrition from the Acharya Ranga Agricultural University in Hyderabad, and his PhD in Biochemistry from the National Institute of Nutrition, Indian Council of Medical Research, Osmania University.